We'll begin today with Dr. Sasha Stump providing a brief overview of the Safer Products for Washington program and our criteria for safer, feasible, and available. Sasha's overview will be followed by a presentation on alternatives work for insulation, solid deodorizers, and floor waxes and polishes. After all three presentations, we'll stop recording and take a 5-minute break. When we return from break, we'll answer questions from the Q&A, then we'll take verbal questions from anyone in attendance. When we're sharing information, we ask that you stay muted so everyone can hear. And now I'll turn the presentation over to Sasha.
Thank you, Michelle. Hello, everyone. Thanks for joining us today. I'm going to turn my camera on briefly again, just so that you can put a face to my name, but then I'm going to turn it off while I present to save bandwidth and ensure my voice comes through clearly. My name's Sasha Stump, and I'm going to start our webinar today by sharing a short introduction on safer products for Washington. So Safer Products for Washington is a program that was established in 2019 to implement Chapter 70A.350 RCW. The goals of the program are to equitably reduce exposure to toxic chemicals from consumer products and prevent their release to the environment. Restrictions and reporting requirements that are implemented by the program are adopted in rule under Chapter 173337. We implement the Safer Products for Washington program on a repeating 5-year cycle, which is divided into 4 phases that you can see on the slide. In phase 1, we identify priority chemicals and chemical classes to focus on. In phase 2, we identify priority products that are significant sources or uses of priority chemicals. Then in phase 3, we determine regulatory actions for those priority product and chemical combinations. And this is where we're at in our current cycle. Then finally, in phase 4, we'll work to adopt the regulatory actions from phase 3 into rule. Once we complete phase 4 of a cycle, we then go back to phase 1, and this 5-year cycle repeats. We're currently in our second cycle of implementation for our program, and you can see the dates that we expect to complete each phase of this cycle on the bottom of the slide. And as I said, we're currently in phase 3 of our implementation process, so we're working to determine what regulatory action we will take for chemicals and products that we identified and prioritized in phases 1 and 2. If you'd like to review our full rationale for why we listed the priority chemical classes or the products that we're going to talk about today, I encourage you to refer to our Cycle 2, Phase 1, and Phase 2 reports, and links to these reports will be shared in chat. Okay, so as I just mentioned, we are currently in Phase 3 of our process where we make regulatory determinations for the product chemical combinations that we prioritize this cycle. And when we're making those regulatory determinations for priority chemicals and products, the department has 3 options to choose from. You can see those on the left of the slide. Our first option is we can restrict the use of a priority chemical in a priority product. Our second option is a reporting requirement where manufacturers would have to report to ecology when they use a priority chemical in a priority product. Or our third option would be to take no action at this time. Now, if we propose a restriction, we must also show that safer alternatives to priority chemicals are feasible and available, and that a restriction would either reduce a significant source or use of the priority chemicals, or that that restriction is necessary to protect the health of a sensitive population or species. And the first question you might ask is, how do we determine what is safer? Safer is defined in our statute as less hazardous to humans or the environment. So with that in mind, we developed a framework, which we call our criteria for safer, to evaluate and compare the hazards of chemicals. Some of the hazards we consider are listed on the slide, and they include things like chemicals associated with cancer, developmental toxicity, aquatic toxicity, or persistence in the environment, among other hazards. Now, when we're looking for alternatives, we're looking for chemicals that are safer than the hazardous chemicals that we've prioritized for work in the program. We think of safer as a spectrum, and so in our criteria for safer framework, we set hazard tiers along that spectrum that indicate significant steps towards use of less hazardous chemicals. We call these tiers our minimum and our additional criteria. These tiers also align with scoring in other hazard assessment methodologies, and so that lets us leverage those other assessments to inform our work. For example, chemicals that have been evaluated using the green screen methodology and that were scored as benchmark 2 can meet our minimum criteria for safer, whereas chemicals that are scored as benchmark 3 can meet our additional criteria for safer. In addition to green screen, we also refer to other hazard assessments, such as those developed by Cyvera and ChemForward, as well as other resources like the EPA Safer Chemicals Ingredients List, or SKIL. For more information and details on that criteria for safer framework, please refer to the documentation that we'll link in the chat. In addition to identifying safer chemical alternatives, we also look to see if we can identify safer material or process alternatives. This is because our statute also defines safer to include a change in materials or design that eliminates the need for a chemical alternative. Although we know this won't work for all chemicals or products that we look at, these types of substitutions can be some of the more preferable ways to reduce the use of harmful chemicals. An example from our past work in the program is when we highlighted digital receipts as an alternative to the use of bisphenols or other chemical developers in thermal paper receipts. Another example is using washable fabrics for certain applications rather than coating fabrics with something like PFAS to add stain resistance. These alternative processes or materials can work in some applications, and so they offer alternative options to consider in addition to reformulating products to use safer chemicals. I also wanted to briefly mention what we mean when we say feasible and available. We define these by referring to the Interstate Chemicals Clearinghouse Alternative Assessment Guide. Feasible in this context means that the alternative is either used or marketed for the application of interest or another similar application. Available means the alternative is currently used for the application of interest or is sold for use in that application at a price close to current. Now, in practice, what this means is we look for products on the market that already use the safer alternatives we've identified, because that's really good evidence they are feasible and available for use in that product type. A few last notes before we move into our presentations on specific products. First, it's important to be clear that while you may see products, trade names, or organizations listed on the slides that you'll see today, these do not imply endorsement by Ecology. We often need to refer to existing trade names or products on the market to demonstrate feasibility and availability for alternatives, but these are meant as examples only. Second, the information on alternatives and potential regulatory actions that we share today should be thought of as a snapshot in time and not as our final work product. We are still actively working to identify alternatives and determine if they are safe or feasible and available, and some of our product categories are further along than others. That also means that we still have time to incorporate input and feedback, and so we really encourage folks in attendance to share information that they think could inform our continued work. So that's the end of my short introduction, and so now we'll transition into presentations from our Safer Products technical team on 3 of the product categories that they've led as part of our work in Cycle 2. The products that we'll have presentations on today are insulation, solid deodorizers, and floor waxes and polishes. As a reminder, these presentations will be recorded and will be made available on our YouTube channel, so we encourage you to go back and refer to them as needed after they're posted following the webinar. At the end of the presentations, we'll also have some time to hear feedback and answer questions about our process. With that, I'll pass to our first presenter, Prajwal.
Thank you, Sasha. Hello, everyone, and thank you all for being here. My name is Prajwal Tuladar, and I'm a Safer Products chemist with the Washington State Department of Ecology. Today, I am providing an update on our alternatives analysis for organohalogenated flame retardants in insulation products. I will keep my camera off for the rest of the presentation. Next slide, please. Priority chemical class in insulation are organohalogenated flame retardants, also referred to as OFRs. Some examples of OFRs in insulation are tris chloropropyl phosphate, also known as TCPP, tetrabromophthalic acid mixed esters, also known as TBPA diol mixed esters, and polymeric OFRs such as brominated styrene butadiene copolymers. The key hazards associated with OFRs include carcinogenicity, developmental toxicity, aquatic toxicity, bioaccumulation, and persistence. Next slide, please. The product scope for insulation is defined in our Safer Products for Washington Cycle 2, Phase 2 report as materials used in buildings to provide thermal insulation between indoor and outdoor spaces or between two indoor spaces. Insulating materials are used in spaces such as attics, ducts, floors, ceilings, walls, foundations, basements, crawl spaces, and slab on grade. Insulation foam types that we looked into include extruded and expanded polystyrene, also known as XPS and EPS, rigid board polyurethanes and polyisocyanurates, or polyiso, and spray foam polyurethanes. These are usually found as rigid boards with or without facers, insulated concrete forms, structural insulated panels, spray foam insulating sealants, etc. Spray foams can be in the form of open or closed cells used to insulate and seal hard-to-reach or odd spaces. Next slide, please. Resources used to define and map chemical functions of OFRs include product safety data sheets, health product declarations, and EPA's CompTox and ChemExpo database. Commercial websites like flame retardant manufacturer websites, commercial insulation manufacturer websites, and chemical safety and consumer production databases, such as the CPID, also list halogenated flame retardants for use in insulation products. This information is also available in peer-reviewed journal articles. Alternatives information was found in commercial flame retardant and insulation manufacturer websites, chemical websites like Special Chem, as well as public databases like Declare and Cradle to Cradle. Our conversations with manufacturer association groups like the American Chemistry Council, Polyiso Manufacturing Association, and Polystyrene Group helped inform us on the halogenated and alternative flame retardants currently being used in the industry. Next slide, please. The primary function of organohalogenated chemicals in insulation is to provide flame retardancy to meet safety standards. Insulation materials are assigned flammability ratings using the ASTM E84 test method by measuring how fast the flame spread index, and how much smoke it generates, also known as the smoke development index. The materials are generally assigned a Class A, B, or C rating. More information on classification and testing can be found in commercial websites of companies certified to do this type of testing. Building codes require products to have minimum flammability ratings depending on the building type and its application space. Chlorinated flame retardants such as TCPP, when used in both spray foam and rigid polyurethanes, also act as a diluent or a viscosity reducer in the processing phase. Next slide, please. While considering feasible alternatives to OFRs in insulation, we must also look at factors such as energy codes, moisture and air barrier properties, and compressive strength, in addition to the flammability ratings, because all types of insulation products are not compatible in all applications. Energy codes assign different R value requirements based on the geographic climate zones, the type of building, and the application space. Insulation products have assigned R ratings that measure their thermal resistance per inch of the material. While the required R value to meet energy codes remain the same for each individual application space, the type of material used determines the thickness required. In general, plastic foam insulation provide higher R values per inch, allowing it for it to meet energy codes with a thinner profile. This is useful in situations where there is limited space. Flammability rating requirements also changes by application space and building type. Most commercial applications with high occupancy require a minimum Class A rating, while Class B ratings can be used in some residential applications. Plastic foam insulation can also provide moisture and air barrier properties, which reduces the need for other materials when sealing and waterproofing. Some applications like insulation under slabs require the material to have some compressive strength. The available insulation options for this type of usage are limited. Next slide, please. In the table are some examples of non-halogenated flame retardants we found that meet or are likely to meet our minimum criteria for safer based on current information from Cyvera, ChemForward, and Green Screen assessments. Triethyl phosphate meets our minimum criteria for safer based on Cyvera hazard assessments and chem-forward assessment. Diethoxyphosphoryl methanol and ammonium polyphosphate meets our minimum criteria for safer based on available green screen and Cyvera assessments. Aluminum hypophosphite likely meets our minimum criteria for safer based on green screen BM2 score listed on the TCO accepted substances list, but we are still reviewing the data on this chemical from other sources to verify its status. Calcium hypophosphite could also meet our minimum criteria based on the use of aluminum hypophosphite as a suitable surrogate. Next slide, please. Non-halogenated flame retardants in the previous slides are commercially available and are listed in the table with their trade names. Commercial flame retardant websites list or advertise these flame retardants as being compatible with the insulation types listed on the table. At this time, I would like to remind everyone that this webinar is being recorded and you'll be able to review the information in the tables presented by pausing the video once it has been posted. Next slide, please. While safer non-halogenated flame retardants are available, their use in insulation is dependent on insulation manufacturers. Inorganic phosphorus-based chemicals such as Everflam, HPAL, and HPCA are advertised as being compatible with XPS and EPS foams on the chemical websites, but industry groups have told us that polystyrene foam products like XPS and EPS with non-halogenated flame retardants are not available in the US market. There are processing difficulties and not enough flame retardancy with incorporating inorganic phosphorus compounds in polystyrene foam. In 2014, EPA conducted an alternatives assessment to brominated flame retardants, HBCD, used in XPS and EPS foam, and polymeric brominated flame retardant was considered to be safer compared to HBCD. This flame retardant is currently used as the industry standard for XPS and EPS foam. Veriqual R100 is a reactive flame retardant that is designed to be a drop-in replacement for TCPP in polyurethane foam. It works very well for rigid polyiso and polyurethane boards in a controlled factory environment and is a safer, feasible, and available alternative in polyiso boards. Triethyl phosphate is another safer, feasible, and available alternative to TCPP in rigid polyiso boards. An insulation product using this as an alternative flame retardant was found in the DECLARE database. Other polyiso boards that do not list any halogenated flame retardants were also found in the DECLARE database. Feasible alternatives to TCPP has not been found in spray foam applications. While chemicals such as Veriquel and triethyl phosphate may be compatible with spray foam, manufacturers have told us that it's much harder to achieve the same flammability rating in spray foam formulations without the use of additional brominated diols, especially in open cell, low pressure spray foam applications. Next slide, please. As mentioned in the previous slide, some feasible polyiso boards with no halogenated flame retardants found in the DECLARE database are listed here. DECLARE label with red list free declaration requires full disclosure for any chemicals at or above 100 parts per million. For the insulation products listed in the slide, the ingredients in the label do not show any halogenated flame retardants. DECLARE label with red list approved declarations have 99% ingredient disclosures. The products listed also do not show any halogenated flame retardants. Next slide, please. Moving on to material alternatives, mineral wool and fiberglass meet our minimum criteria for safer. They are listed as a full green circle on EPA's safer chemicals ingredients list. These are inherently flame-resistant materials used as insulation. They are also sometimes used as components in some plastic foam insulation products. Even though mineral wool and fiberglass meet the minimum criteria for safer and have a Class A rating, they may not be feasible in all applications. Other materials we are still evaluating include sheep's wool, hemp fiber, wood fiber, cellulose, expanded cork boards, and magnesium oxide cement spray foam. Some of these seem to use boric acid and borate-based chemicals as flame retardants, which does not meet our criteria for safer. Next slide, please. Some examples of mineral wool and fiberglass products that are feasible and available are listed on the slide. Mineral wool products with cradle-to-cradle gold material health certification and declare red list free label are safer, feasible, and available. Fiberglass products that are red list approved without any halogenated flame retardants are also listed on the slide. The examples provided are not exhaustive, and you may also look for other insulation products that are red list free, red list approved, or cradle-to-cradle gold material health certified on their respective websites. Link to these websites will be dropped in the chat. Next slide, please. In summary, we have identified rigid polyiso polyurethane boards with no organohalogenated flame retardants that are safer, feasible, and available. Chemical alternatives to flame retardant TCPP in spray foam insulation are safer and available, but not feasible. Chemical alternatives to brominated flame retardant for XPS and EPS polystyrene foam are also safer and available, but not feasible. Material alternatives such as fiberglass and mineral wool are safer, feasible, and available, but may not be compatible in all applications. Next slide, please. Based on our current information, we are likely to propose a restriction to organohalogenated flame retardants in rigid polyiso polyurethane foam insulation. We have not yet identified safer, feasible, and available alternatives in spray foam polyurethane and polystyrene insulation, and we do not have enough information to propose a restriction. We are still evaluating some material alternatives for safer and for applicability. Alternative analysis for this product category is expected to extend into cycle 3. Next slide, please. I would appreciate any feedback on our assessments. In particular, if there are any information on halogen-free spray foam that we may have missed, would be appreciated. If there are any additional considerations for feasibility and availability we need to look at, and any suggestions for additional resources or information can be sent to our Safer Products for Washington email address listed on the slide. Thank you all for your time, and I will pass it on to our next speaker, Sean.
Thank you so much, Prajwal, for the update on insulation. Thank you, everybody. Hello, my name is Sean Ziga. I am a chemist with the Washington State Department of Ecology, and I too will be putting my camera off for the remainder of this update. Without further delay, today I will be providing an update and overview on the research associated with the current chemical product combination of concern, along with alternative chemicals and products, specifically brominated and chlorinated compounds in solid deodorizers. Next slide, please. To begin this overview, the chemical class here references brominated and chlorinated organic compounds. Specifically, we are concerned with 1,4-dichlorobenzene or paradichlorobenzene. This volatile organic compound is found in solid deodorizers and possesses hazards that are associated with carcinogenicity, aquatic toxicity, as well as eye irritation. Next slide, please. To elaborate on the scope that is encompassed by this product category, we have defined solid deodorizers here to include all things that function as a toilet, garbage, or urinal deodorizer, or a solid continuous action air deodorizer or freshener. Do note, however, that this product category does not include deodorizing products that are sold as liquids, packs, powders, or are intended to fully dissolve in water. Next slide, please. The functions associated with this priority chemical were ascertained from various sources. Alternative chemistries that can then serve the function of this priority chemical were also evaluated using similar sources. A review of the scientific literature, as well as publications and other available data of relevance for this particular product category, provided references that are cited on later slides, particularly the OECD data for functional and product use categories, product data associated with alternatives and products containing 1,4-DCB that were found in the Mintel Global New Products database, as well as California's Air Resource Board assessment of paradichlorobenzene in solid air fresheners, as well as just a general internet search for various publicly available information from manufacturers and various retailers. Next slide, please. The primary function of 1,4-dichlorobenzene in this product category is as a deodorizer. This function and intended use within these products aims to reduce the concentration of unwanted scents and odors in a given space. The OECD document that was previously referenced was used to help aid and define the chemical function and product use scoping. Here they define deodorizers and deodorizing agents as substances that reduce or eliminate unpleasant odors and protect against the formation of malodors on body surfaces. Next slide, please. This table shows a list of candidate chemicals that are likely or do meet our minimum criteria for safer for the use and replacement of the function of 1,4-dichlorobenzene in these solid deodorizer products. These chemistries include non-nanoform carbon, sodium bicarbonate, clinoptilolite, as well as camphor, which is currently being evaluated for meeting our minimum criteria for safer at this time. Next slide, please. This table shows feasible and available products. These are example products that use the aforementioned chemistries, and this is evidence of the feasibility and availability of the products on the market containing these alternative chemistries to brominated and chlorinated substances and 1,4-dichlorobenzene specifically. Products here listed are intended to cover a wide range of applications for deodorizing uses, such as bathroom-specific or general space deodorizing. Next slide, please. A potential material alternative exists where alternative bioenzymatic blocks and similar products are currently feasible and are available on the market. These products contain bacteria that are slowly released with multiple flushes as a means of odor removal and mitigation. At this time, the evaluation of these odor eliminating products and ingredients is underway to determine whether or not they meet our minimum criteria for safer. Next slide, please. As a safer process alternative for specific deodorizing applications, such as in urinals or similar bathroom systems, ice can be used to mitigate the need for a deodorizing product, as the melting of the ice will dilute the concentration of malodors that are present. And it will also lower, as a function of reducing the temperature, it will lower the volatility of malodorous substances as the ice melts, which will inhibit the proliferation of odors over time. It also acts as a diluent, slowly flushing away residual urine. Next slide, please. A process alternative that involves the use of specific certified cleaning products, namely EPA certified safer choice products, in spaces that would require or may need a solid deodorizer, would be a way of mitigating the need for deodorizing as a process in general. This table provides a list and examples of products that cover a wide range of deodorizing applications that could be used for various surfaces and deodorizing spaces to reduce and mitigate the need for deodorizing products in general. Please reference this table as well as any other information that was shown during this webinar at a later date, and do remember that these brands are not necessarily reflective of endorsement by Ecology. Next slide, please. Based on these findings, alternatives are both feasible and available, with products containing chemistries that do meet Ecology safer criteria. Therefore, evidence does exist for the restriction on the use of 1,4-dichlorobenzene, as currently safer and feasible and available alternatives do exist. Next slide, please. With that being said, thank you so much. We would like to solicit any feedback and considerations that we may need to take into account at this time. And if we have missed anything, please refer to the Safer Products wa@ecy.wa.gov email for any and all information that you can help us provide. And with that being said, thank you for the opportunity. And I will pass it to my colleague, Yvonne, who will begin to talk about PFAS and floor polish and floor waxes. Thank you.
Thank you, San. Thank you, Sean. Good afternoon, everyone. My name is Ivan Titale, and I am a safer products chemist in the Hazardous Waste and Toxic Reduction Program in the Washington State Department of Ecology. I am happy to see you here, and today I will provide an update on the priority products of floor waxes and polishes. I will turn my camera off and begin my presentation. Next slide, please. The priority chemical class for floor waxes and polishes were per and polyfluoroalkyl substances, or PFAS. Revised Code of Washington, or RCW 78.350.010, Section 10, defined PFAS or PFAS chemicals as, quote unquote, a class of fluorinated organic chemicals containing at least one fully fluorinated carbon atom. The link to this RCW is provided in the chat. In floor waxes and polishes, fluoropolymer, such as PTFE, and fluorosurfactants, such as 6,2-dipap, could be used. As previously laid out in Cycle 1 Implementation Phase 3 report of Safer Products for Washington, key hazards of PFAS included carcinogenicity, reproductive toxicity, developmental toxicity, bioaccumulation, and persistence. Next slide, please. We define the scope for floor waxes and polishes in Cycle 1.5 Implementation Phase 3 report of Safer Products for Washington to include products designed to polish, protect, or enhance a floor surface. Examples of these products included multi-surface floor finishes, low gloss, semi-gloss, and high gloss polishes. Next slide, please. As a first step in our alternative analysis, we defined the chemical functions of PFAS in floor waxes and polishes. To obtain this information, we relied on three resources. The first one was the Safer Products for Washington Cycle 1.5 Implementation Phase 3 Technical Report. The second one was a draft report from California Department of Toxic Substances Control, or DTSC, entitled Product Chemical Profile for Floor Maintenance Products Containing Perfluoroalkyl or Polyfluoroalkyl Substances. And the third one was a presentation by BASF entitled Replacing PFAS in Water-Based Floor Care Coatings. Next slide, please. Based on the three sources mentioned in the previous slide, we determined the following functions for PFAS in floor waxes and polishes. As protectant, which can be further defined or mapped as water repellents or oil resistance or repellents. PFAS in floor waxes and polishes can also function as surfactant and wetting agent, both of which can increase the spreading abilities of components in a product formulation. Next slide, please. In addition to the three sources that are previously mentioned, we also use the following resources when we perform alternative analyses for PFAS in floor waxes and polishes. Special Chem, Node, and UL Ultras Prospector were used to find alternative chemicals with the same functions as that of PFAS. We also use these websites for feasibility and availability analyses, specifically to determine the trade names of potential chemical alternatives. Comtox product reuse categories and collected data on functional use were also utilized to find alternative chemicals with the same functions as PFAS. The product reuse categories listed under EPA's Comtox platform are broad, but an example is given in the chat based on a keyword search of quote-unquote floor polish. Web searches were performed to determine the feasibility and availability of chemical alternatives, specifically to find example material safety data sheets, or MSDSs, for floor wax or polish products that contain chemical alternatives. And lastly, EPA Safer Choice products were considered for safer process alternatives. Next slide, please. We sent manufacturer orders to 5 companies on December 2025. The companies are required to provide responses 6 months from the date the order was received, which would be around June 2026. In this order, we asked for information on floor wax and polish products currently offered for sale in Washington, as well as all PFAS and non-PFAS alternative chemicals used for the functions of surfactant, wetting agent, and protectant. The industry has been responsive as we have received some responses. We are currently still processing them, so we were not able to include this information in time for the webinar. Next slide, please. This slide contains the list of safer chemical alternatives that we have determined to meet ecology's minimum criteria for safer. Chemical names, their chemical abstract surface registry numbers, or CASRNs, and functions are listed as the headers for each of the columns. Paraffin wax, carnauba wax, and dimethicone can provide water repellence function. With respect to dimethicone, we noted that this chemical was previously considered as safer during cycle 1.5 of Safer Products for Washington, particularly if the cyclic volatile metal siloxane monomers were less than 1,000 parts per million or ppm. Next slide, please. Silica gel, precipitated, crystalline free, can provide oil resistance function, while triethoxyoctylsilane can provide oil repellence function. Next slide, please. 5 chemical alternatives can provide the function of surfactant and wetting agent. The chemicals are diethylene glycol monobutyl ether, diethylene glycol monoethyl ether, ethylene glycol monobutyl ether, dipropylene glycol monomethyl ether, and alcohols C12 to 16 ethoxylated. Next slide, please. In terms of feasibility and availability, this table lists the safer chemical alternatives, example of chemical trade names, and examples of floor waxes or polishes that use the safer chemical alternatives. While I would not have the time to go through every chemical line by line, audience can always go back to the recording of this presentation and hit pause to examine this list closely. Note that we omitted the company names for brevity. And also, further, note that we have not yet found an example floor product that contained triethoxyoctylsilane in its list of ingredients without the additional presence of PFAS. Next slide, please. Our proposed safer process alternative was based on our previous works in Safer Products for Washington, cycles 1 and 1.5. Specifically, a safer process for the oil resistance or repellent functions could be to wash or clean the oiled floor with EPA Safer Choice certified cleaning products. Note that EPA Safer Choice certified products are considered as safer products according to our criteria for safer. Examples of such products are listed on this slide. Next slide, please. In summary, we believe that we have identified multiple safer alternatives to PFAS in floor waxes and polishes that met ecology's minimum criteria for safer. We believe that safer alternatives are feasible and available for all of the functions of PFAS. Therefore, current information that we have collected supports a restriction on the use of PFAS in floor waxes and polishes. Next slide, please. Having said that, we still welcome feedback from interested parties. A question for this priority product includes, is there an example use of triethoxyoctylsilane in floor wax or polish product that we can cite? Certainly without the addition presence of PFAS in the list of ingredients. You can send your feedback to the listed email address. This ends my presentation, and I thank you for your attention. I will now give the stage back to Michelle.